Hello, my name is Kunjumon Vadakkan. I study the nervous system to understand how it operates. I have a conflict of interest to declare. In the previous presentations, we have seen the importance of deriving a hypothesis that can explain all the findings of the nervous system at various levels. We have seen that learning and memory can be used as a representative nervous system function that can be used for such studies. So today in this presentation we will see what type of changes can occur during associative learning and how first person virtual inner sensations can be induced using those changes at the time of memory retrieval. We have seen that there are no cellular changes occurring at the time of memory retrieval. Therefore, from whatever changes that occur during associative learning, we expect that a passive reactivation of those changes will give rise to the induction of first person inner sensations. So let us see key changes that can take place. Let us associate two sensory stimulus S1 and S2 through the sensory receptors. They reach the neuron N1 presynaptic terminal, postsynaptic terminal, which is also called the spine, propagates further to reach its neuron, second neuron N2, and then we are reaching the locations of convergence. So let's draw it with a different color here. S2 sensory receptor reaching its neuron, let us call as N3 presynaptic terminal, postsynaptic terminal, N4 presynaptic terminal, and its postsynaptic terminal. Based on semblance hypothesis, the key changes are occurring at the locations of convergence of these two stimuli. So we have to find a key feature at this location of convergence that can take place at the time of associative learning. Let us first figure out where such changes can take place. These are presynaptic terminals and these are postsynaptic terminals, which are otherwise called dendritic spines. First, let us see to which neurons are these dendritic spines belonging to. Can they belong to the same neuron or different neurons? For different reasons, they are expected to belong to two different neurons. The reason number one is that if they are belonging to the same neuron, then in order for a change to occur between these two spines, we need to have isolated electrical cables that can be formed between these two dendritic spines at the level of the dendritic branch. But we do not have any specific mechanism to form specific associative signature that occur between these two dendritic spines at the level of the dendritic branch there. The second reason is that studies using pyramidal neurons have shown that the diameter of these dendritic spines on a dendritic branch are smaller than the interspine distance. In other words, the interspine distance is, on an average, they are greater than the spine diameter. Therefore, a physical change to occur between these dendritic spines should belong to two different neurons. And the third reason is that if this sensory stimulus is inducing a motor action, so say for example it is going to its neuron, say let's name it as N5, and if this N5 is connected to a muscle or a motor unit there, let us imagine that the S2 is going to a neuron, it been 6, and it has its own connection to motor units that can evoke a behavioral motor action. Then after associative learning, if these two spines belong to the same neuron, they cannot express specific motor actions. So for all those reasons, it is expected that these dendritic spines that are expected to be physically abutted to each other, in order to generate a mechanism between these two dendritic spines, they should belong to two different neurons. So based on semblance hypothesis, a mechanism is expected to take place between these two dendritic spines, and it was named as postsynaptic functional link. At this point, we don't know the nature of that interpostsynaptic functional link, but we are going to derive the nature of that interpostsynaptic functional link. Now, between these two spines, there is extracellular matrix there. We can call it as extracellular matrix space. So basically, the lipid membrane studies have shown that as we bring two lipid membranes closer to each other, there will be water of hydration between these two lipid membrane dendritic spines, or in other words, it's called hydration repulsion. Hydration repulsion. In other words, we can say that there is water of hydration there that separates those two dendritic spines. So a very high energy is required to exclude that water of hydration and bring those two dendritic spines in physical contact with each other. Bringing them in physical contact with each other will make electrical depolarization to spread from one dendritic spine to the abutted dendritic spine. Since high energy is required to exclude this water hydration, it's a very highly reversible process, and so it is going to last only for a short period of time. So let us draw that picture here again. So here we have presynaptic terminal, this is the postsynaptic terminal. So let us use this color. The presynaptic terminal, this is the postsynaptic terminal, and let us draw a physical contact between these two dendritic spines after the removal of water hydration. So these are abutted to each other, so there is removal of water of hydration. So it's a highly reversible process, and it's only going to last there for a very short period of time. So if we can use that interpostsynaptic functional link to explain induction of units of internal sensation of one of the stimulus by the arrival of the second stimulus at the time of memory retrieval for a short period of time, then that's a good mechanism for working memory. Whereas if we can have a mechanism that keeps those interpostsynaptic functional links for long time, then we can explain short-term memory. Say for example, these are lipid bilayers. So I'm going to draw bilayers here. If these dendritic spines can be enlarged by certain mechanism, then these dendritic spines can undergo hemifusion, partial and complete hemifusion. So let us draw hemifused postsynaptic membranes here. So enlargement of the dendritic spines can lead to hemifusion between, that is hemifusion between the dendritic spines. Again, hemifusion is a reversible process. So initially there will be a partial hemifusion stage which will then convert to a complete hemifusion stage. So if you draw double membranes here, we will see that this is a double membrane of lipid bilayer. We will see 4 layers here if you take a cross section here. Now because of the hemifusion, there are only 2 membranes there. Again, this stage can reverse back to single isolated dendritic spines, but hemifusion will last for longer period of time compared to that occur by the removal of water hydration. So this can be a good mechanism that can explain short-term memory. If one of the cue stimulus can induce virtual first-person inner sensation by a mechanism that we are going to see in a few minutes. Hemifused membranes can undergo a stabilization process. If a transmembrane protein is inserted across that hemifused area, then it can remain stable there until that transmembrane protein is removed. So this is a stabilized hemifusion. This is a stabilized hemifusion. So this, if it can last for a long period of time, this can explain long-term memory, provided the reactivation of this interpostsynaptic function link can induce virtual first-person inner sensation of the second stimulus. So we are going to see that mechanism in a few minutes. The good part of this mechanism is that it can be induced by associative learning. It can be reversed back for different durations of time. It can be reversed back very quickly, explaining working memory, and it can last for short period of time, explaining short-term memory. It can last for long period of time, explaining long-term memory, provided there is a mechanism whereby one of the stimuli can induce virtual first-person inner sensation of the second stimulus. So let us see whether we have a mechanism, a key feature at these locations to explain the induction of virtual first-person inner sensation. Let us see what is taking place at these synapses on a baseline state. In a baseline state, there is quantal release of neurotransmitter molecules from single vesicles all the time. That is taking place all the time, depolarizing a portion of the dendritic spine membrane. So that is the default state of the synapses. Occasionally, an action potential will arrive from the axonal hillock towards those presynaptic terminals and will induce postsynaptic potentials, which is a very huge potential which will propagate through the dendritic spine neck towards their neuronal soma. So baseline state is quantal release all the time, even while sleeping, and occasional arrival of action potentials there. Now let us see what is going to happen at the time of memory retrieval. Let's say that we exposed the nervous system to the sensory stimulus S1, and let us call it as a cue stimulus. When stimulus S1 arrives at this dendritic spine, it is going to reactivate this interpostsynaptic functional link, and the depolarization will propagate towards its dendritic spine and towards its neuronal soma and will evoke a motor action. That postsynaptic potential will also propagate through the interpostsynaptic functional link and traverse towards the dendritic spine, which is interlinked with the first dendritic spine, and that will also propagate towards its neuron and will reach the motor system. So the cue stimulus is now reactivating the interpostsynaptic functional link, depolarizing the dendritic spine and propagates towards the neuronal soma. If this neuronal soma is already at a subthreshold activation state, short of just one depolarization from one dendritic spine, then it can trigger an action potential, and it can fire an action potential and cause motor function. So now we can explain the behavioral motor activity that is induced by the cue stimulus or one of the stimuli that took part during the associative learning. Now the second part that we have to explain is that how can it induce a virtual first person inner sensation of the second stimulus. The second stimulus is not there, but the first stimulus has to induce a virtual first person inner sensation of the second stimulus. Do we have a mechanism here to explain that? Now let me talk about a context for explaining the virtual first person inner sensation. We have already started thinking about the necessity to explain a virtual first person inner sensation to occur at the time of memory retrieval. It was Marvin Minsky who was the founding director of MIT's Unit of Artificial Intelligence. He, back in 1980, published an article called K-Lines, A Theory of Memory. A Theory of Memory. In the journal Cognitive Science, volume 4, pages 117 to 126. So in this paper, which is available freely, he envisioned that in biological systems, the cue stimulus should be capable of inducing a cellular hallucination of the presence of or the arrival of the second stimulus, which was associatively learned in the past. So there should be a mechanism that can explain the formation or the induction of a cellular hallucination of the associatively learned second stimulus in its absence. So the question is, do we have a mechanism that can explain whether the arrival of the first stimulus S1 at this presynaptic terminal can induce a virtual first person inner sensation of the second stimulus? That's what we are going to see here. If you have a mechanism, then that's of paramount importance, because we have to explore it further to understand the operation of the nervous system. It's going to be really difficult in the beginning, because we are now going to talk about a cellular hallucination. We are going to talk about something that is virtual in nature. And for a third person experimenter, that first person property is not accessible. So a third person cannot access that first person property. Whatever we are going to talk right now is virtual in nature. As I have explained in our previous presentations, that we were comfortable in dealing with large number of virtual items in the past. For example, negative numbers. Our sensory systems do not have any access to atoms or subatomic particles or electromagnetic waves or large number of field properties, but the evidences indicates their presence. So here in neuroscience, we have to do this exercise to find out a mechanism which is universally present throughout the nervous system that can induce virtual first person inner sensations. And that's the beginning stage of our search for the first person properties within the nervous system. So we should be really curious to explore it. So do we have anything that can suggest the induction of a first person inner sensation at the arrival of one of the sensory stimulus? What we have got is an interpostsynaptic functional link there between the dendritic spines. Now, as I said before, at the synapses, there is quantum release of neurotransmitter molecules from the presynaptic terminals towards the postsynaptic terminal, and it depolarizes this membrane, the spine head. It depolarizes. So it's a very small depolarization that is taking place only at the spine head region, but it is taking place all the time, even while we sleep. That's a default state. Occasionally there will be an arrival of an action potential at this presynaptic terminal, releasing a volley of neurotransmitter molecules, inducing postsynaptic potentials which propagate down towards this neuronal soma. So this is the background default state of the system, and in that background default state, now the Q stimulus is arriving here and it is propagating through this interpostsynaptic functional link towards that second dendritic spine here. So in this default state, any incidental activity of this second dendritic spine from the lateral aspect, which takes place occasionally only, that such an activity, for such a lateral activation, is expected to induce a cellular hallucination that something is coming from its presynaptic terminal. So again, I will repeat, the background state is that the synapse is receiving quantum release all the time. For this dendritic spine, it is receiving quantum release of neurotransmitter molecules from its presynaptic terminals all the time. In that context, a single lateral activation will induce a semblance of arrival of activity, from its presynaptic terminal, where in fact nothing is coming from its presynaptic terminal. So now we have to discover what is the sensory quality of that cellular hallucination that is being induced at this dendritic spine head. So this is completely new concept that we are thinking at this point, because there is quantum release taking place all the time. In that default state, a single lateral activation is expected to induce a cellular hallucination at this membrane region that it is receiving an activity from its presynaptic terminal, where in fact nothing is coming from its presynaptic terminal, thereby evoking a cellular hallucination or a semblance of arrival of activity from its presynaptic terminal. So that is completely a cellular hallucination. Now we have an expected mechanism of cellular hallucination. We have to explore and find out what is the content of that cellular hallucination. What is the sensory identity or sensory content of that cellular hallucination. So from now onwards, whatever we are going to find out here is completely virtual in nature. So unlike the neurotransmission that we were talking all this time, which are real, the properties of that virtual inner sensation that we are going to extrapolate and find it out is completely virtual in nature. We were not used to dealing with any virtual items in the past in neuroscience, but this is the first time that we are going to extrapolate and find out the sensory identity of that cellular hallucination. So what is this dendritic spine hallucinating about? The content of the hallucination should be the activation of the sensory receptors that it is connected to. So it is hallucinating about receiving activity from the sensory receptors. So sensory receptors are getting activated. So which sensory receptors? To know that, we have to extrapolate from this dendritic spine all the way towards the sensory receptor level. Usually from the locations of convergence, it takes 3 to 5 orders of neurons to reach up to the sensory receptor level. So how can we do that extrapolation? So this presynaptic terminal is belonging to a neuron here. Let's call it as N4. N4. We have learned from the previous presentations that a neuron N4 can be activated, or a spike can be induced at the axonal hillock, or it can undergo action potential by activation of any 100 of inputs out of around 30,000 inputs that it can have. So we already discussed that neuronal firing is not specific with respect to the inputs. A set of any 100 dendritic spine activation can provide summation of sufficient potentials at the axonal hillock to give rise to an action potential. So sets of any 100, it can be 40 even, 40 dendritic spines close to this neuronal soma can also give rise to an action potential. So we can say nearly 40 to 100 out of 30,000 inputs, if they summate spatially or even temporally, can induce an action potential here. So that is what this dendritic spine is hallucinating about. So it can be 40 to 100 out of 30,000. So a large number of inputs can give rise to the activation of that neuron. What about their activation? So these inputs, they are also coming from neurons at lower orders. So we can say that is N3, the orders of neurons at that order. So these neurons are also receiving inputs from nearly 40 to 100 inputs out of nearly 30,000 of their dendritic spines. So it's going to expand much larger than this one, because it can receive inputs from a large number of dendritic spines, and that can lead to the firing of this neuron in this neuronal order. So similarly, if we can extrapolate further up, we will get another layer, and finally after 3 or 4 neuronal orders we will reach the sensory receptor area. So we are going to get a very large sensory receptor area whose activation can lead to the activation of this synapse and the depolarization of this dendritic spine. So again, this is a completely new exercise in neuroscience, whereby we are trying to find out the sensory content of the cellular hallucination that is being induced at this interlinked dendritic spine, which is now depolarized by the Q stimulus S1 through the interpostsynaptic functional link. So from here onwards, nothing is real, everything is virtual. We have to extend our imagination to find out the sensory content of the cellular hallucination. That's what we are doing. So there is nothing in real, but what we are extrapolating is based on the existing synaptic and interpostsynaptic functional links that are existing at these orders of neurons. So we are trying to extrapolate back towards the sensory receptor level to find out those sensory receptors whose activation can lead to the depolarization of this dendritic spine, because those sensory stimuli that can activate those sensory receptors will be the content of the cellular hallucination that is taking place at this dendritic spine. Now we have to ask the key question: do we need to activate all those sensory receptors to depolarize this dendritic spine? We need not necessarily have to activate all of them. Maybe a subset of those sensory receptors should be able to propagate through these neuronal orders and arrive at this dendritic spine. So let's find out this minimal subset of sensory receptors whose activation can lead to the depolarization of this dendritic spine. And let's find it out, find the packet of, this is the packet of virtual sensory stimuli that is capable of activating that sensory receptor subset whose activation can lead to the depolarization of this dendritic spine. Now the question is, how do we know about this sensory receptor subset? if we know the existing synaptic connections from the sensory receptor level all the way up to this dendritic spine, and if we also know the interpostsynaptic functional links that are existing at these neuronal orders, then we can extrapolate and find out the minimum sensory receptor units whose activation can lead to the depolarization of this dendritic spine. And from that sensory receptor subset, we can arrive at a packet of virtual sensory stimuli, a minimum sensory stimuli that is capable of activating this sensory receptor subunit, and that was named as semblyon. So these are the basic virtual units of inner sensation that is being induced at this dendritic spine. So now we have large number of such semblyons at this level that can lead to the depolarization of this dendritic spine. Now we have to ask the question whether when the cue stimulus arrives, such packets of virtual inner sensations are not only taking place at this interlinked postsynaptic dendritic spine, it is taking place at large number of locations where interpostsynaptic functional links have formed. Now let's find it out how the qualities of the sensory stimulus S2 is induced within the nervous system from these packets of virtual sensory stimuli. Now we are expecting to have a natural computational process that is taking place at physiological time scales from using these semblyons to arrive at this a framework of virtual sensory quality of the item S2 whose memory is being retrieved. So that is a natural computational process which we have to understand yet. Computational process that is taking place at physiological time scales. So this is going to be a systems property. This is going to be a systems property. This is going to be a systems property. Systems property of what type of systems? Systems where when we put electrodes at the extracellular matrix space, there is oscillating potentials at the extracellular matrix space. So in those systems, this natural computational process occurs between the semblyons that are induced at large number of interlinked spines to generate the framework of virtual inner sensation of the second sensory stimulus. Now, what is so specific about this oscillating frequency? This oscillating frequency has component both vertical as well as horizontal. That's how we get oscillations. And we know that synaptic transmission can give rise to one vector component of the oscillation. What about the perpendicular vector component? If you look carefully here, now we have, I will show it here, we have one synaptic transmission taking place at the synapses, and the transmission of potentials across the interpostsynaptic functional link takes place perpendicular to the synaptic transmission. So that can contribute to the second vector component of the oscillating potentials. Both the induction of virtual units of inner sensations as well as their computational process that is taking place at physiological time scales is expected to be a systems property of those systems that have extracellular oscillating potentials whose frequency depends on the vector components that are contributed by both the synaptic transmission as well as the transmission of potentials across the interlinked postsynaptic terminals. Any changes in this frequency will prevent the induction of those units of inner sensations. So the frequency of extracellular potentials is very specific to the type of the nervous system. Now, if you look at from here to the sensory receptors, we can see that this graph is going this way. It is expanding towards the sensory receptor region, and we have units of packets of virtual inner sensations which we called as semblyons here. Now, the computational process is expected to take place by using these semblyons that are generated at various locations similar to this, at these locations of interlinked dendritic spines. So we have to get the final product that is a framework for the sensory qualities of this item whose memory is getting retrieved. So for example, let me draw the shape of this item as a star. So if this is the star, the sensory quality of the item whose memories are getting retrieved, then this feature, this framework has to be formed by the computational process that takes place from large number of units of semblyons that are generated from various levels, from interlinked postsynaptic terminals. So we don't know the exact computational process, but we can deduce that all these semblyons should get computed to form this framework for the second stimulus. At least it should be an area where semblyons from different interlinked postsynaptic terminals should converge. At least convergence of semblyons at one location is one of the likely property of that computational process. But still we don't know what exactly is the computational process. But what we know is that once we know the synaptic connections, once we know the interpostsynaptic functional links that are there between these neuronal orders, then we can deduce all the semblyons from the minimal sensory receptor activation that will depolarize this dendritic spine. From that knowledge of semblyons that are taking place at various locations of these interpostsynaptic functional links within the nervous system, we have to find the computational process that give rise to this S2. So since we have the knowledge of all the semblyons from a given nervous system, it is easy to find out the computational process that will finally give rise to the shape of or the framework of the sensory property of S2 within the given system. So our next steps to make progress in this area is to find out that computational process. So I sincerely hope that you understood the derivation that has been carried out and the unique features of the synapses that receive counter release of neurotransmitter molecules all the time, and when an interpostsynaptic functional link is induced at the locations of their convergence at the time of associative learning, those interpostsynaptic functional links can then be reactivated to induce units of virtual inner sensations. Now, one thing is clear, those interpostsynaptic functional links have to stay there in order for the cue stimulus to induce units of virtual inner sensations. In the case of working memory, since the removal of water hydration can induce an interpostsynaptic functional link only for a very short period of time, the arrival of one of the sensory stimulus after a certain period of time cannot induce memory of the second item. Whereas if the interpostsynaptic functional link is formed by hemifusion, then they can remain there for a short period of time, during which one of the cue stimulus can arrive and induce virtual inner sensation of the second stimulus, leading to short-term memory. And if you can stabilize those interpostsynaptic functional links for a long period of time by the insertion of a transmembrane protein there, then we can keep that for a long period of time, explaining long-term memory. So I sincerely hope that you understood the beauty of the formation of interpostsynaptic functional links, their different durations of maintenance, and a novel mechanism for induction of virtual inner sensations that can contribute to the memory, and the natural computational process that takes place at physiological time scales as a systems property of those systems that have oscillations of extracellular potentials whose vector components are in fact getting contributed by both the synaptic transmission and the perpendicular transmission of potentials across the interlinked postsynaptic terminals. I sincerely hope you understood. If you have any questions, please feel free to email me or ask me below this video. I will be happy to answer them as much as I can. Thank you for watching and have a great day.